Okay, right. So let's continue our engineering mathematics lecture for the week of this new topic for this week is solutions to homogeneous and non-homogeneous second order ordinary differential equations, or ODE. Okay, so in this week, at the end of this week or at the end of this lecture, you should be able to do the following. So you should be able to develop the strategies to solve second order linear ODE with constant coefficients only. And to do this, to solve the second order linear ODE with constant coefficients, we can do first one is the homogeneous second order ODE, linear ODE, where we will use the characteristic equation. And for the non-homogeneous second order linear ODE, we will use two methods, which are the method of undetermined coefficient and the method of variation of parameters. So we will go through these three things this week. Okay, so you know that there are homogeneous and non-homogeneous ordinary differential equation ODE, especially for the linear ones. Okay, so for homogeneous ODE, as you can see, first we need to arrange the ODE into the standard format, which is the coefficient multiplied by the second derivative, the highest order derivative, followed by the lower order derivative until y only, the independent variable in terms of the dependent variable. In this case, y is the dependent variable and x is the independent variable. And as you arrange this and you want to put everything on the right hand side that contains only the independent variable and any constant, and if it is equal to 0, then you say that this ODE is homogeneous. So the solution to this homogeneous ODE is known as the complementary solution YC. So C here stands for complementary. Okay, so for example, the solution to this given ODE here, d2y over dx squared minus 4 dy dx plus 3y equals to 0. And yeah, we will work this out, how to get this solution. But an example here is given. So YC, the complementary solution only for this homogeneous ODE is here, C1 times exponential to 3x plus C2 times exponential of x. Whereas for non-homogeneous ODE, at the right-hand side here, it's not 0. So there's a function of x, Rx here, or a constant. Okay, so it's just a function of the independent variable x. So the solution for this non-homogeneous DE is a combination of a complementary solution YC and particular solution YP. So here in this case, the solution to this ODE here, so here we have this same DE like what we have for the homogeneous part, except that at the right hand side it's not 0, but rather it is a function. So to this function, the solution to this ODE is YC plus YP. And then as you can see, the YC here is the same for the solution to the homogeneous part. Okay, so the YC here is the same with what you have here. So this is your YC, but because this is a non-homogeneous ODE, so you've got to add the YP, the particular solution. So this part here is your YP because it is non-homogeneous. But we will go through how to solve for both homogeneous and non-homogeneous. All right, so before we go to the strategies, we need to know some concepts, okay, some terminology. So first, we need to go through this general theory of linearity principles and linear dependency, right? So, okay, given that the solution to this ODE is like you can see just now, okay, so this is the same ODE like you saw in the previous slide. So the solution is YC equals to C1 e to the 3x plus C2 times e to the x. So now we want to verify that YC equals to C1 E3x plus C2 EX is the correct solution to the DE. Okay, so if we assume the solution is Y1 equals to E3x, and if we assume the solution to be just Y2 equals to e to the x, and if we combine the solution Y1 and Y2 into YC equals to combination of Y1 and Y2 with some constants here, So you can do the verification of solution like what we did in the previous week, where if you want to verify the given function as a solution to the ODE, then you need to deduce an ODE from here. So, well, you can start with this simple example first. So y1 is equal to e to the 3x. So then dy1 over dx is what? 3e 3x, and d 2y over dx squared equals to 9 times e 3x. Then you can substitute this into the given ODE. So d2y over dx squared is 9e 3x minus 4 times dy dx is 3 e 3x and plus 3 times y. So y is e 3x. So if you just do the maths here, so 9 minus 12 plus 3 is 12 minus 12, so you get 0. So e to the 3x is a solution for the given ODE. Likewise, you can repeat the same step for e to the x, and when you substitute into this ODE, you will also get equals to 0. And if you want to further satisfy your curiosity, you can also take this, the whole yc here, and deduce what is yc over dx and what is d2yc over dx squared, the second derivative with respect to x, and put it inside this ODE. I can guarantee you that you will get equal to 0 as well. So we can say that all these given solution y1, y2, and yc are the solutions to the ODE equation. So they are the true solution to the ODE. Okay, so we want to know what is the linearity principle and principle of superposition. So the complete solution is formed according to this linearity principle or principle of superposition as follows. So if you have y1 and y2, there are both the solutions to the homogeneous linear differential equation, then so is the solution yc equals to c1y1 plus c2y2, where c1 and c2 are arbitrary constants. So in conclusion, the general complementary solution of the homogeneous linear differential equation is equal to y equals to c1y1 plus c2y2. So y in this case is a function of x, where y1 and y2 are also the solution for the equation, and they are linearly independent to each other. They have to be linearly independent to each other. So how do we check whether y1 and y2 are linearly independent to each other or not? So that we will do in the next steps. Okay, so how to check? So if two solutions are linearly dependent, it means that these two solutions are redundant. So there are not actually two given solutions, there is only one solution, because one of them are dependent. One of them is dependent to the other solution. Hence, they do not represent two independent equation or two independent solution. So we need to have two linearly independent solutions of y1 and y2 in order for us to get a complete solution for the given second order ODE. Okay, so we can use these following methods to check whether the two solutions are linearly independent to each other. So the first method is the linear dependency theorem, and the second one is the Wronskian method. So let's go through the first one, which is the linear dependency theorem. So in this theorem, you can check if y1 and y2 are linearly dependent or not just by looking. So, okay, so let's say if you have c1y1 plus c2y2, it can only be equal to 0 when c1 and c2 is not 0, meaning, in other words, y1 and y2 are proportional to each other, because, okay, c1 and c2 are constant. By right, they couldn't be equal to 0. We don't want the combination of c1y1 plus c2y2 equal to 0. However, if c1 and y1 can become equal to 0, even when the value of c1 and y1 is not equal to 0, meaning y1 and y2 are linearly dependent. They are proportional to each other. We will see an example after this, okay? However, if y1 and y2 are linearly independent, Then if we just put C1y1 plus C2y2, it can only be equal to 0 when the value of C1 and the value of C2 is equal to 0. So in other words, y1 and y2, they will not become 0 unless C1 and C2 is equal to 0. So y1 and y2 are not proportional to each other. Okay, so let's use the linear dependency theorem to check if these functions are linearly dependent or not. So let's do that in the whiteboard. Okay, so check the linear dependency of the given solution. Given, yeah, this one. Okay, let me just copy this. Put it here. Make it bigger. So we want to check if y1 and y2 are linearly dependent or not. So here, so we have y1 and y2, so we can write down c1y1 x plus c2y2 of x is what? So c1y1 is c1 times e to the x plus c2 times 2e to the x. So you can see that c1 e to the x plus 2 times c2 e to the x. So here, this expression can be equal to 0. When can this expression be equal to 0? It is when c1 plus 2, c2 equals to 0, c1 equals to negative c2, and vice versa. And it could be that this equation can be equal to 0 when c1 equals to negative 2 and c2 equals to 1, one of the options, one of the possibility. It could be any value as long as c1 is equal to negative 2 times c2. So whatever value you put in the c2 value and you put into c1, and then when you put it inside this expression, you will get it to become equal to 0, meaning that this whole thing here will be equal to 0 even when C1 and C2 are not equal to 0, meaning they are linearly independent to each other. So let's just put it this way, yeah. Okay, if it's equal to 0, then C1EX equal to negative 2 C2EX, meaning this is proportional to each other. You see, like e to the x is negative 2 c2 over c1 e to the x. So this is a proportionality constant of the two functions, so y1 and y2. So they are not linearly independent. They are not independent equations. They are not independent solutions. So that's why we say that in this case, y1 equals to e to the x and y2 equals to 2 times e to the x are actually linearly dependent. So yeah, we don't want that in our solution for second order ODE. What we want are the two sets of equations which are linearly independent. Okay, so next example is to check if the y1 equals to e to the x and y2 equals to e to the 3x. Check if they are linearly dependent or not. So we can write down c1y1 plus c2y2 to be equal to c1 e to the x plus c2 e to the 3x. Okay, so a shortcut here, you just look at the this value, the exponential value here. So if in this case, it's one is x, one is 3x, so it's impossible for them to be linearly dependent to each other because they are of different exponential. So this term will not, they will not become equal to 0 unless C1 and C2 itself are 0. Okay, can you see? So C1 plus C1 times e to the x plus C2 times e to the 3x, it will not ever become equal to 0 unless C1 and C2 are themselves equal to 0. So we say that y1 and y2 are linearly independent and they are not proportional to each other. Okay, so let's say if you end up with y1 and y2 like this in this example here, so what do you do if you're given this solution to the ODE, which are linearly dependent equations? So what do you do? What do you have to do if you obtain two linearly dependent solutions? So if that is the case, then you need to put in extra effort to make one of them to not be linearly dependent to another. So for example, in this case, you can propose that y2, you can put another x term in front, so 2x ex, such that this now y2 will not be dependent on y1 because y1 is just e to the x. So 2x times e to the x will not be ever linearly dependent to e to the x. So that is the extra effort required if in case you are presented with two linearly dependent solutions. So that is one method to determine whether the given solution is linearly dependent or not. Okay. So another method to check the linear dependency of the solution is to use the Wronskian method. So in this case here, let x be the independent variable and y is the dependent variable. So okay, so we define this Wronskian determinant as, so you put it into a matrix here, y1, y2, dy1, dx, dy2, dx. So you evaluate the value of y1 times dy2 dx minus y2 times dy1 dx. Okay, so if this value, if it's equal to 0, then we say that y1 and y2 are linearly dependent. So if you compute the Wronskian method from y1 and y2 and the value of the Wronskian determinant is not equal to 0, then you can say that y1 and y2 are linearly independent. So this is a bit more straightforward for you to determine whether or not y1 and y2 are linearly dependent or independent. So we can use the same equations just now, although we already know the answer, but we want to demonstrate to you how to use Wronskian method instead to determine the linear dependency of these equations. Okay, so we use whiteboard. Okay, so yeah, y1 is e to the x and y2 is 2ex. So you find dy1 dx, here is e to the x, and dy2 dx is 2 times e to the x. And you calculate the Wronskian determinant. So y1, dy1 dx, y2, and dy2 dx. So you put in the numbers or the expression e to the x, 2ex, and 2ex as well. So then you multiply and minus, then you get equal to 0. So since the Wronskian determinant is equal to 0, thus y1 and y2 are linearly dependent to each other. And the second example, okay, same example that we had before. So y1 is equal to e to the x and y2 is e to the 3x. So from y1, dy1 over dx is ex, and dy2 dx is 3x. So you compute the Wronskian determinant. So y1 is ex, dy1 dx is dx, y2 is e3x, and the derivative is this. So you calculate, so you get this times this minus this times this, so 3e4x minus e4x equals to 2e4x, which is not equals to 0, whatever the value of x is. Thus, because the Wronskian determinant is not equal to 0, then we concluded that y1 and y2 are linearly independent to each other. Okay. Right, so let's take a quick break here before we proceed to the second part of the video.